Okay, this is a Chapter 5 check, and the first question says, tell how many significant figures are in the following. So if you look at the first one, you have a bunch of leading zeros, that is zeros that are before the first non-zero number. So leading zeros are not significant, so we don't count those. So we start with 2. The zero between the two non-zero numbers is always significant, so we have 1, 2, 3 for this one. In the second one, we have a number beginning with 7, and there's a bunch of zeros in the middle, and then ending with a 6 and a 7. All of those are significant because the zeros in between non-zeros are always significant. So we have 1, 2, 3, 4, 5, 6, 7, 8 in that one. In this one, 40.0450, people had a little bit of trouble with this one. The zeros in between the non-zero numbers are always significant. Nobody had a problem with that. This zero right here is a trailing zero, but it is significant because the number has a decimal in it. Anytime you have a number with a decimal, the zeros after it are going to be significant. So this is going to have 1, 2, 3, 4, 5, 6 significant figures. And in the last number is 9,500. We have 2 trailing zeros. When you don't have a decimal, these zeros are not significant, so this one would have 2 significant figures. Okay, express these numbers in scientific notation. We did have a few people who had some trouble with this. So let's look at the first one, 430. The first thing you need to do when you do scientific notation is figure out how many sig figs you have. So for 430, this number does not have a decimal, so the trailing zero here is not significant. Therefore, it only has 2 sig figs. So I'm just going to put 2SF here to help us remember. So when we start writing in scientific notation, the first thing we have to do is express the number as a number between 1 and 0. That means you're going to put your decimal between the first 2 numbers here. First 2 non-zero numbers. So the decimal is going to go between the 4 and the 3. So we're going to write 4.3. Now, once you've written that new decimal, you have to move over however many places it takes to get to where the understood decimal is. So for the number 430, we understand that the decimal is really at the end of the 0 here. So we're going to take this new decimal and we're going to move 1, 2 spaces in the positive direction. If we have a number line here, and this is the negative direction, and this is the positive direction. Okay? So this is 2 powers of 10 in the positive direction. So we're going to write 4.3 times 10 to the second to indicate that we moved over 2 powers of 10 to the end of that number. Alright, so now you look at the next one, and that's 430 with a decimal there. The decimal there tells you that that 0 is significant. So this number is going to have 3 significant figures. So when you begin to write the first part of your scientific notation, you're going to write 4.30 because that 0 is significant. Now once again, your decimal goes between the 4 and the 3, just like I've written here, and you're moving out the same direction, 1, 2, to the end of where the decimal, this one actually has a decimal, so you move to where the decimal actually is. So for this one, it's still going to be 4.30 times 10 to the second. So the difference between the first one and second one only has to do with the decimal changing the number of significant figures you have. Now in the third example, we have 0.00430. So the leading zeros we know are not significant, and the trailing 0 is significant because the number has a decimal. So this one too is going to have 3 significant figures. So this one we're going to start out the same exact way as we did in the second one. We're going to put our decimal between the 4 and the 3, but we're going to move back 3 spaces to where the original decimal is. So we write 4.3, and we're moving back 3 powers of 10 So this is going to be times 10 to the negative 3. That's a decimal there. All right, so 4.3 times 10 to the second, 4.3 times 4.30 times 10 to the second, 4.30 times 10 to the negative third. All right, now in the fourth example, this one's a little bit more complicated because you already have a power of 10 in the problem, but you don't have this first number written in the proper form. Remember, you have to write it as a number between 1 and 10. Now this one has 4 significant figures. That's pretty easy to see because there aren't any zeros to complicate things. And we're going to put our decimal between the 2 and the 6. And then you're going to move in the direction of the original decimal. So for this one, you're going to move 1, 2 powers of 10. So we're going to write 2.672, and we moved over 2 spaces, so that's 10 to the second. And we also have another times 10 to the second. So in this problem, we have now 2.672 times 10 to the second times 10 to the second. This 10 to the second results from moving the decimal. This 10 to the second is part of the original problem. Now, when you multiply powers of 10 together, basically what you do is you add their exponents. So we end up with something like this, 2.672 times 10 to the 2 plus 2. This 2, the first 2 represents 10 to the second, and the second 2 represents the other 10 to the second. All right, so you add those 2 together, and you'll get your final answer is 2.672 times 10 to the 4th. If you have forgotten how to do this, go back to the appendix in the back of your book. It has an explanation for it. If you still have trouble, look it up on the internet, go back and review it in an old math book. We're going to be using this a lot, so you need to make sure you understand how to do it. All right, then looking at our last example, we have 0.0354 times 10 to the negative 3. So in this one, our number is smaller than 1. We have 3 significant figures. The leading 0 is not significant. So 3 sig figs. And you're going to put your decimal between the first 2 non-zero numbers, so that's going to go between 3 and 5. So we're going to write 3.54. Now you move your spaces, your powers of 10 back in the direction of the original decimal, so we're going to move back in the negative direction 1, 2 spaces. So that's going to be times 10 to the negative 2. Now we also have in the original number times 10 to the negative 3. So we take these 2 powers of 10 and we're going to add the exponents together, and we'll get 3.54 times 10 to the negative 2 plus negative 3. And when we add negative 2 and negative 3 together, we get negative 5. So our final answer is going to be 3.54 times 10 to the negative 5. Okay, for the word problems, the first one is convert 86.03 times 10 to the 4th milligrams to kilograms. Give your answer in scientific notation. And the instructions before that also tell you to show all of your work and use appropriate sig figs. So you got 3 things to think about here as you're doing these problems. So we have 86.03 times 10 to the 4th. That is not in the appropriate scientific notation, but it doesn't matter for working the problem. You want to just go ahead and start with what you're given. Now, a lot of people, well, not a lot, but some people took this number and wrote it out 860300. And that is the number. That's not incorrect. And they worked the problem like that. However, we're going to be using a lot of big numbers with a lot of powers of 10 as the year progresses. So you need to go ahead and make sure you know how to put this number in your calculator if you don't already, because you don't want to spend the whole year trying to convert all these numbers to these big long numbers that we're going to be working with. So if you have a TI 83 or 84 or even a new TI 30, you probably have a second EE function that works very nicely for inputting these numbers. So what you would do is take the number that you're given, 86.03, and then you have a little button on your calculator that says second on it. And so you're going to press that second button. Okay, now you have another number on your calculator, and most likely it's the button above the 7. I don't know for sure, but that's the way it is on all of mine. And on that button, it says, it has a little symbol on it, depending on the calculator. I don't know what the symbol will be. But above that button, it says EE. Okay, so what that means is when you press the second button and then you press this button, you will get the EE function. And the EE function is just this 10 to the power function. So you're going to press your second and then EE. All right, and then you press in the power of 10 that you have, which would be 4. Okay, so put it in on your calculator like this, and that should input that number for you just like that. If you have a different kind of calculator, some of the older calculators, the EE button is not a second function, so you might just put it in 86.03 EE. I have a calculator that does like this. I actually like it better because it's one less button to press, and then put the 4. All right. So make sure you know how to do these, how to input these numbers on your calculator. Practice it and learn it before the test, because it was just going to make your life so much easier. So let me erase that and now just work the problem. Okay, so going back, you start with 86.03 times 10 to the 4th, and we want to set it up in the dimensional analysis or the factor label method that I showed you. So you put that, and be sure and put your units in all of these that you're working. It'll make your life easier in the long run. Now we've got to get milligrams to kilograms. All right, so our conversions are, we know that 1,000 milligrams is equal to 1 gram, and then 1,000 grams is equal to 1 kilogram. So these are our equivalencies that we're going to use as conversion factors. So we're going to go from milligrams to grams first, and then from grams to kilograms. So we put milligrams on the bottom, 1,000 milligrams, and 1 gram on top. And then you've got to go from grams to kilograms, so 1,000 grams on the bottom and 1 kilogram on the top. After you set this up, then you input this number, 86.03, second EE, most likely 4. That will put the number in for you, divided by 1,000, divided by 1,000. And my calculator went ahead and gave it to me in scientific notation, and it gave me 8.603 times 10 to the negative 1. So that would be your answer. Also, don't forget to put your units on there, kilograms. Okay, and go back and check and make sure your units cancel. If you set it up like this and your units cancel, you will end up with the right units for your answer. This is a really good way to set your problems up, because if you set everything up right, everything cancels out properly, and you pretty much know you've done it right. I know that it seems kind of long and involved to set things up like this, but we're going to be doing some very long, complicated problems later on, and if you go ahead and learn it now, you're going to save yourself some grief. So even though you might have gotten the right answer, if you didn't set it up the way I asked you to, I took off for it, because it's really, really important that you learn to set these problems up properly. Okay, for the next problem, calculate 4.6 times 7.107. divided by 1.4 plus 36.44. This is pretty simple. You put the top numbers into your calculator and you can add the bottom numbers, and you can just take the top divided by the bottom. The main consideration here is to figure out how many sig figs you're going to have. You're going to be limited to 2 sig figs because of this 4.6 that you're multiplying by. So when I multiply the top number, I get 32.6922. Remember that you don't put your sig figs in until the very end and your final answer. So you're going to keep everything you've got until the end. So we have that number, and then we're going to add 140 and 3644 together, and that gives us 37.82. When you plug those numbers into your calculator, you may get something like 0.863958. But remember, you're limited to 2 sig figs, so all of this is going to be dropped. You're going to round down because the 3 is less than 5. So that gives you 0.86. Then once again, it said to give your answer in scientific notation. So this number the decimal has to be moved to between the 8 and the 6. You take that decimal and you move back to the original decimal, so you're going in the negative direction. So that gives you 8.6 times 10 to the negative 1. And that would be your final answer. Okay, so the next problem is convert 200 degrees Fahrenheit to degrees C. It wants you to show all your work and also write the formula. So I have the formula here. I think everybody did fine getting the right formula. Okay, so you take 200, which is the temperature of the Fahrenheit, subtract 32 over 1.8, and that gives you 168 divided by 1.8. And that actually gives you 93.333. Since your original number is a whole number, go ahead and give your converted number as a whole number, 93. 200 really, technically that's one significant figure, but because we're working in whole number degrees for temperature, I think it's probably better just to use the same convention. So if your temperature that you're converting is 1 place past the decimal, go ahead and give your answer as 1 place past the decimal. If it's 2 places, give it as 2 places. Just follow whatever convention your original temperature has. And also don't forget to put your degrees C on there. Okay, for the last problem, calculate the mass of a sample which has a density of 2.34 grams per milliliter and a volume of 5 milliliters. Write the formula and show all your work. So you should know, hopefully, that density equals mass divided by volume, and they want you to calculate the mass, which means you have to solve for m here. So to do that, we're going to multiply both sides by v. The v's cancel, and you get v times d equals m. Okay, and most people didn't have any trouble at that point. So we're trying to find mass, so we say m equals d times v. We're given a d of 2.34 grams per milliliter. Put your grams, put your milliliters down here. Please put your units in the problem. It will save you a lot of mistakes later on. So your 2.34 grams per milliliter times the volume, which is 5.00 mils. Okay, now if you set it up properly and you put your units in, then you see that your milliliters will cancel. And your answer is going to be in grams, which is what mass is. Grams is a mass measurement. I had several people give the answer as milliliters. Milliliters is not a mass measurement, it's a volume measurement. And if you put your units in here properly and cancel everything out, you will not make a mistake like that. So, put your units in. It's very, very important. This mass density problem is very simple, but when we start doing very long problems, you've got to put your units inside the problem so that you get the right answer when you come out on the other end. Okay, so 2.34 times 5, you input that in your calculator and you get 11.7. And that has 3 significant figures, which works out really nicely because both of these other numbers that you used have 3 sig figs, and your answer is going to be in grams. Don't forget your units. So that's the final answer for that last problem.